In section 3.1, we will review exponents and logarithms. First off, logarithms and exponents are inverses of each other. So if you have log base b of a equals to x, we can write that in exponential form as b to the x equals to a. The base of the logarithm becomes the base of the exponent, and the x and the a, they reverse. So the x becomes the exponent, the a becomes the answer. There are two special cases. Ln, which is a natural log of a, is equivalent to log with base e. E is an irrational number, kind of like pi. If the base of a log is not written, then the base is assumed to be 10. Here's an example. Write the following logarithmic equations into exponential form. So our rule says that the base of the log, which in this case is 3, becomes the base of the exponent. The 81 and the 4, they reverse. So the 4 becomes the exponent, and the 81 becomes the answer. So in exponential form, 3 to the 4th equals to 81. When we have ln, that's a natural log of 6 equal to x, remember that natural log is just log with a base e of 6 equals to x. So if we are to rewrite this into exponential form, the base e becomes the base of the exponent. The x and 6 reverse, so e to the x is equal to 6. If the base is not written, it's assumed to be the standard base, which is base 10. So this is rewritten into exponential form as 10 to the second power equals to 100. Going the other way, b to the x equals a is equivalent to log base b of a equals to x. Once again, the base of the exponent becomes the base of the log, and the x and a, they reverse. Again, two special cases. If our exponential form is e to the x equals to a, then in logarithmic form, the base of the exponent, which is e, becomes the base of the log. But when we have a log base e, that's actually the natural log. So whenever we have an exponential form of e to the x equals to a, that's actually log base b, which is ln, or natural log of a, equals to x. 10 to the x equals a, we have log base 10. A and x reverse, so we have log base 10 of a equals to x, except we don't write base 10, so it just becomes log base a equals to x. As an example, write the following exponential equations in logarithmic form. The base of the exponent is 5, so this becomes log base 5. The 125 and 3, they switch sides. This becomes log base 5 of 125 equals to 3. E to the x equals to 19. We have log base e of 19 equals to x. The base of the exponent e becomes the base of the log. The 19 and x, they reverse. Log base e is the natural log, so this is natural log of 19 equals to x. Finally, we have log. The base of the exponent is 10, so we would say log base 10. The 3 and 10,000, they reverse. So we have log base 10 of 1,000 equals to 3. However, we don't write the base 10, so this is just log of 1,000 equals to 3. Next, if m and a are positive real numbers with a not equal to 1, and r is any real number, then the following rules apply. First one is the power rule of logarithms, which basically says if we have log base a of m to the r, where r is the exponent of a term of a logarithm, then the r comes to the front. So we never leave an exponent in a logarithm. The exponent always gets rewritten as a coefficient, and it comes to the front. So in this case, we have log base 3 of x to the 5th. In logarithms, we don't leave exponents, so the 5 is going to come to the front, and this becomes 5 times log base 3 of x. Next, we got the product rule of logarithms. Log base a of mn equals to log base a of m plus log base a of n. So in other words, if we have a single logarithm and we're multiplying two terms, or it could be 3 or 4 or 5, when we separate these, so now each term is going to get its own logarithm. So we're going to split these up into separate logarithms. Then multiplication turns into addition. Here's an example. We have log base 4 of x squared y to the third. This equals to log base 4 of x squared plus log base 4 of y cubed. In other words, when each of the terms gets their own logarithm, the multiplication turns into addition. And by the power rule, the exponents have to be rewritten as coefficients. They go to the front. So this equals to 3 log base 4 of x plus, or 2 rather, sorry, 2 log base 4 of x plus 3 log base 4 of y. Quotient rule says if we have division under a single logarithm, when we write these as separate logs, so each term gets their own logarithm, then division turns to subtraction. For example, if we have log of 15 over x to the fifth, this equals to log of 15 minus log of x to the fifth. When we separate these into each individual logarithm, the division turns to subtraction. And so this gives you log 15 minus 5 log x. The exponent of a logarithm always comes to the front and becomes a coefficient. Next, let's combine the product and quotient rule. So notice what's happening. If you're multiplying two terms, then that multiplication turns to addition. If we're dividing, then anything that's being divided turns to subtraction. So if we divide two terms, they both will have a negative sign. In other words, they both get subtracted. And whatever's on the numerator, this turns into addition. So if I were to expand this, I have log of x plus log of y to the fourth. These two are on the numerator, so they both have positive signs. Any term that's being divided will have a negative sign. So it'll be minus log of b to the fifth. This is also being divided, so minus log of c to the seventh. If we simplify this a little bit further, the exponents have to come to the front. So this is log of x plus 4 log of y minus 5 log of b plus 7 log of c. The next formula is quite commonly used. It is a change of base formula. Most calculators can only handle logarithms with base 10. However, what if we want to find a logarithm that is not base 10? Let's say we have base 3. In that case, we have to apply the change of base formula, which basically says this. It says that if you have log base b of m, it equals to log of m over log of b. And then when we do this, they both change to base 10. That way we can put these in a calculator. So if we have log base 3 of 15, according to the change, we can't just put this in a calculator because our base isn't 10. So according to the change of base formula, this equals to log of 15 divided by log of 3. Now this we can put in a calculator because when we change the base, both of the bases become base 10. If you put this in a calculator, you'll get 2.4650. If you want to check to see if this is correct, you just have to turn this logarithmic equation, which is log base 3 of 15 equals to 2.4650, into an exponential one and see if it's true. So I take my base, which is 3, I raise it to the power of 2.4650, and I want to check, does that equal to 15? And if you put this in a calculator, you'll get very close to, you won't get exactly 15 because we rounded the 2.4650, but we will get very close to it. Next property, if you have log base b of b, so the base and the term we're taking the log of are both the same, then this equals to log of b over log of b according to the change of base formula, and that's equal to 1. So in any time our base and the term we take the log of are the same, our answer is always 1. So log base 5 of 5 is going to equal to 1. Now we're going to go backwards and write this as a single logarithm. So when we go backwards and write it as a single logarithm, first off, the coefficients, they go back to where they came from, because remember, we're going backwards to a single logarithm. So this becomes log of 7 to the 4th minus log of x to the 5th. And our objective is to write this not as two separate logs, but combine them under one logarithm. So here's what we know, that if we divide two terms, that turns to subtraction. So if we're going backwards and we're subtracting two terms, that goes back to being a division problem. Or you can think of it like this. Any term with a positive sign is going to go on the numerator. Any term with a negative sign is going to go on the denominator. So this equals to log of 7 to the 4th divided by log of x to the 5th. Or this is one term, log of 7 to the 4th over x to the 5th. And note that we have a single logarithm now and not two separate logarithms as we did before. Next example, write as a single logarithm. Once again, first thing is all the coefficients, they go back to being exponents. The 1 we don't have to write because 8 to the 1 is 1. So this gives us log of 4 to the 3rd plus log of x to the 2nd minus log of 8 to the 1st, which is just log 8. And now we want to write these all under one single logarithm. So here's, again, one thing to remember. Anything with a positive sign will go on the numerator. So the 4 cubed and the x squared, both of these have a positive sign, therefore they go on the numerator. The 8 has a negative sign, therefore it goes on the denominator when we go from 3 separate logs to one log. And we can simplify this a little bit further. 4 cubed is 4 times 4 times 4. That's log of 64 divided x squared divided by 8. 64 divided by 8 is 8, so this actually equals to log of 8x to the 2nd power. Next example, we're going to expand this. We're going to write that as a sum of our difference of logarithms. So we have log of x cubed plus log of y to the 4th. Anything on the numerator is going to have a positive sign. The z to the 7th is on the denominator, therefore that'll have a negative sign. And all the exponents that come to the front become coefficients. So we have 3 log of x plus 4 log of y minus 7 log of z. Okay, next write as a sum or a difference of logarithms. So this is equal to log of x to the 16th plus log of cube root of y to the 17th. Now we know that any radical form, we convert that into exponential form. So I'm going to rewrite this as log of x to the 16th plus log of y to the exponent becomes the numerator and the root becomes the denominator. The 16 comes to the front, so does the 17 thirds. So this equals to 16 log of x plus 17 over 3 log of y. In the next video, we will learn how to solve logarithmic and exponential equations.